useful when I was learning the method. Now, most synchrotron experiments do this. You get photons out of the synchrotron. This could be white, this could be pink, this could be monochromatic. And you're wondering what pink is, right? Have you? So who can say what is a pink radiation, actually? When you use a mirror, you cut off the high energy, which is blue. The left is remaining is pink, right? So if you send, let's say, 20 kilovolt X-rays onto a mirror and put the mirror at some angle, you cut off everything above 20 keV. So the hard part is gone, the soft part is left. So that's why we call this pink. Sometimes we use a monochromator. Giorgio showed one example today to select the wavelength. So let's say some monochromatic radiation is coming, hitting your sample. You may put an electron detector here to do some science, like called photoelectron spectroscopy. You can put a film in the forward direction, which is what Röntgen did in 1895, right? Got a picture of his wife's hand with the ring, and that's called absorption imaging. You can put your detector at an arbitrary location as long as you know what angle you have put in. That's called scattering. Right? You can then sweep that angle so that you will find that there are some spots where X-rays are very strong, called diffraction. So all of these techniques give you something about the sample. You can also look at fluorescence that is coming out. Fluorescence means that you have sent photons, you have knocked out some electrons, some other electrons fell into their place, and the difference in the energy is emitted as a fluorescence light. All right? The person who developed this method, Henry Moseley, was killed in the Gallipoli War, right, in 1915 at the age of 27, the year he was supposed to get the Nobel Prize. Right? 1915, I'm sorry. So, nevertheless, each of these detection mechanisms can be used for imaging, can be used for tomographic reconstruction, can be used for chemical imaging. So it's actually, the arena is quite big. That's why on a ring like APS where you have 70 beam lines, each one can still find itself something unique to do. So you can say, give us an example. I will give you a few examples. All right? For example, if you take this electron detection and send it to a hemispherical electron analyzer, which is something all ESCA machines in your labs have, all right? You can then take a single crystal, measure this along certain crystallographic directions, and you will find out that angle resolved photoemission spectroscopy will give you the Fermi surface. And there are new things called whale fermions or whale fermion crystals. These are objects that were predicted through theoretical means by high-energy physicists at the turn of the century, last century, and it took 100 years to find them in the the counterpart in the solid-state physics. And you can say, why should I care about a whale fermion? You should, because the electrons go with the speed of light inside the solid, all right? Which means fast electronics. So even though it sounds like a theoretical construct, but it has immediate material implications. You can do you can do diffraction. When you do diffraction, of course, you can solve the structure of crystals. But if you do a nice diffraction, if you are really good at it, and those are not physicists, they are actually biologists who are good at it, they can solve 50,000, 60,000 atom structures. These are the G receptors which led to the Nobel Prize. You can find exactly where those atoms are. All right? So even though the method of diffraction is old, Bragg and von Laue in 1915, but over the years people learned how to do it correctly and efficiently, and then they came up with something called multiple anomalous diffraction, which takes advantage of the tunability of the X-rays. This is something you cannot do in your lab. Sometimes the crystals are too big, like DNA or your viruses, and you want to know the shape of it. So you can study the shape by doing something called small angle scattering. If you are a company developing a bulletproof vest like DuPont or Dow Chemical, you need to know how this nylon that you're producing has texture. So this is the kind of method you can use to develop all kinds of new fabrics. With the modern two-dimensional detectors, you can actually take this data in less than milliseconds, so you can do time-resolved small angle scattering to look at evolution of a chemical process, for example. This one I'm going to talk about in the next slide, so I will skip this at the moment. And you can also do something called X-ray absorption spectroscopy, which most of you are familiar with, X-rays or X-ups, to look at and this is a method where an electron is knocked out, and now your electron becomes your probe because it scatters from the nearby atoms, which gives you these oscillations, and then you take Fourier transform of these oscillations to find out about the first, second, third near neighbors. And the information in the near edge gives you quite a bit about the valence state and the coordination number of the materials you're interested in. And you can also take an insect inside an amber, you can measure all of its properties, you can look at its lungs, you can measure its oxygen ability, taking ability. You can even say, if you know the age of this, what was the percentage of oxygen in the air 3 million years ago, you might be able to say something about that. So if you're a paleontologist or evolutionary biologist, this kind of data is almost impossible to get with any other method. And you can also do some cell biology, drug treatment, and so on. So I will skip the rest. Now, if you look at now a little closer to the scattering, you can find out that there are so many different things that goes on inside the solid. Right? There's something called Compton scattering, which differentiates valence electrons from the core electrons. As you know, electrons in the atoms are in the shell, but when you put them together and make a solid, some of the electrons go into the valence band, like in metals, and they spread out. And can you tell the boundary between those electrons that are valence, those electrons that are core? And so Compton scattering allows you to get the Fermi surface, all right? But in Compton scattering, you lose about 1,000 eV or so, all right, maybe 10,000 eV. Which means you need 100 kilovolt X-rays to do that. And so a source like Sesame is out. You cannot do that in a 2.5 G machine. You can also look at core electron excitations, which is what we do for X-ray Raman scattering, for example, or X-ray absorption spectroscopy. You can look at plasmons. You can look at electron hole excitations. You can look at magnetic oscillations called magnons, phonons, which is what I'm going to look at today. Or you can do elastic scattering, which is called diffraction or quasi-elastic scattering. So each of these is a separate instrument and a separate career and a separate beamline. So if you have a beamline that does this, you cannot do that. If you have a beamline optimized for this, you cannot do that. So that's why these beamlines are dedicated for a specific purpose. So multi-purpose beamlines usually end up being moderate, not very successful. So to summarize, if the incident beam energy coming in and going out is the same, that's what we call elastic scattering. If they are different, we will call inelastic scattering. If it changes direction, then in addition to energy transfer, there will be momentum transfer. And depending on the degree of momentum transfer, you will be looking at either continuum excitations or you will be looking at excitations between the two atoms. All right? So therefore, this is you will see this figure many times in your career, but each time you will understand that there's more to it than what is shown on the figure itself. Now this is another very complicated plot. I apologize, but since there are so many physicists in the room, in their interest, I will explain. This is again 20 orders of magnitude in energy transfer. As you see, it's possible to go all of that in a synchrotron. All right, you can't do that in the lab. And this is also momentum transfer in the logarithmic unit. So these are different inelastic scattering methods like X-ray Raman, Compton, interresonance scattering, neutron scattering, photon correlation spectroscopy, and interresonance forward scattering. So each of these depend on what you do. For example, if you are in infrared, you cannot transfer too much momentum because the energy is very low, and therefore you will be looking at the center of the zone, so you cannot get into the Brillouin zone region. And Brillouin zone is a wonderful concept solid-state physicists developed in the 1930s. It's a way of reducing all of the periodic lattice into one lattice, into one unit cell. because everything in one unit cell is repeated in all other unit cells. If you understand the behavior in one unit cell, you'll be able to understand behavior in all of the unit cells. That's an invention of human brain, really an amazing concept, and that falls right here. So a lot of the techniques are developed to study this region because that's where all the solids are. So why should we care? Why should we actually study solids using inelastic scattering? Well, you can measure sound velocity. Now you can say, well, you know, aren't you bored measuring the sound velocity? Well, we all deal with earthquakes, or we all deal with atomic bombs. When Pakistan explodes a bomb, in Europe or in the United States, somebody measures the seismic oscillations and look at the amplitude and say, this was a 2.5 kiloton bomb. All right? So if you're a person who is interested in national security and world politics, of course you care about the sound velocity as the sound travels through Earth. Because as we know, when you go deep, the pressure increases, the temperature increases, so all the minerals that you have studied, the values are useless because you have to know the pressure and the temperature dependence of the sound velocity. And that's where synchrotron radiation comes quite handy. If you're a theorist calculating the thermodynamics of Earth or thermodynamics of the moon or the thermodynamics in a plasma generator, you need to know vibration entropy, specific heat, things like that. If you're a geochemist, and I will show one example of this, you might be interested in the isotope fractionation because an object that's coming from the moon, like the moon rocks, if you look at the iron 57-54 ratios and compare them on Earth, they are not the same. Right? So when the moon was forming, or when it was ripped off from Earth, what was the oxygen partial pressure that actually led to this fractionation? And so that's something you can measure using synchrotron radiation. And compression tensor, Young modulus, some of you engineers particularly would know that this is an important parameter. But if somebody says, I have cholesterol in my vein, and therefore I have hardening on my veins, you say, can you measure it? Like, how much cholesterol causes how much hardening? Which means you have to measure the stiffness of your lipid bilayers with cholesterol intercalation. And so you have to come to us because we can actually measure that. All right? And so on. So these are all parameters that goes into understanding solids, and you need inelastic scattering method to do that. So how do you do it? I'm going to skip a few slides because I see that I'm losing my audience. So I'm going to show you how we actually will measure it, all right? So there are many models that you have to study when you do lattice dynamics, so I'm gonna spare you from these details. But let me show you how we are going to be able to measure this in an instrument, all right? So this is something called phonon dispersion curves. Has anyone studied solid state physics? Obviously you have, right? And you have seen these graphs before, right? So if you have a single crystal, you can actually measure phonon dispersions point by point. If you use the nuclear resonance scattering, you can actually measure this entire thing using phonon density of states. And once you have phonon density of states, most of the additive properties of thermodynamics come into play. So the instrument we're going to use was this. This is the baby version of our instrument. All right, this was a student PhD thesis. And then we built a real one, twice as big, also twice as large in number of analyzers and better resolution. And how does it work? This is the real instrument, so it's not a simulation in the theory, but this is the practical instrument. It's 9 meters long. So the sample is staying in this blue dot, can be your sample. You scatter X-rays, it goes into 4 pi. Some of it will go through these pinholes into 9 analyzers. These are spherically bent silicon analyzers, 12, 12, 12 reflection of silicon, which reflects the X-rays back onto themselves. So Bragg angle is 90 degrees, so it's 180 degree Bragg angle. Each of these crystals are specially made to send the beam focused back onto these 9 detectors. So each one is at a different momentum transfer value. So in the Brillouin zone, you can cover the entire Brillouin zone with this. And then if you want to go and make some sweeps in the first, second, third Brillouin zone, this is like the world's most expensive Fourier transform machine. Right? So it takes about 2 years to plan, draw, and procure this system. I mean, and then we put about $1.5 million to build this system. It's one of the 3 instruments in the world that has this capability. Right? So we use this to study things like this, for example. This is hot solid silicon. This is supercooled silicon at 13 degrees C. Now, silicon is an interesting object because when it is crystalline, it's a semiconductor. And when it is liquid, it's a metal. The coordination number in the covalently bonded crystals is tetrahedral, right? We have 4 bonds because there are 4 sp3 orbitals in silicon. In the liquid case, however, this coordination goes from 4 to 6 and it breaks down, the covalency breaks down. So how can I get supercooled silicon? If the melting temperature is above 1300 degrees, you can take a crystal of silicon suspended in air or in argon atmosphere, you send a laser light on the top, and then you wait and heat it up at any temperature you like. We can go as high as 4000 degrees in the lab. All right? And then, since it is containerless, you can cool it down and you can avoid the nucleation, and you can go down supercooled liquid. So if you go to supercooled liquid, still there are some collective excitations which we can measure as a function of momentum transfer. And then the sound velocity peaks, they appear here. So if I look at the sound velocity of the hot solid silicon, that's 7.3 kilometers per second. Supercooled silicon is 4.5 kilometers per second. Now you can say, why is this such an important thing? For example, we take sapphire, we measure the viscosity of sapphire, and if you are in the rocket fuel business, you know that sapphire has the highest energy per unit volume or weight of any material. So if you're going to lift a 100,000 ton rocket to send something to the moon or Mars, you need to know the viscosity of sapphire at 3000 degrees, and there are not very many good ways to measure it, right? So even though the method is very sophisticated, the problem that we are applying to are very mundane but very relevant to technology. Now you can say, why don't you use neutrons? How am I doing with time? Another 20 minutes or so? Are you okay? You guys are bored or you want to go home? Hungry? Okay, I still see some smiling faces, which means I haven't exceeded my welcome yet. So if you use neutrons, because that's another option, right? Why don't you use neutrons? There is a region in the dispersion curve between energy versus momentum transfer where neutrons cannot work. If the velocity of sound is bigger than the velocity of the neutrons, there is not enough momentum to measure it. So this is a forbidden region for neutrons, and it happens that almost 90% of liquids are in this region. So if you're a liquid physicist, you may forget using neutrons because most of the time you will not be able to. Now, one reason I went to Argonne was really the Mössbauer spectroscopy. So how many of you have heard Mössbauer effect? 1. Excellent. I'm not asking you, Kostas. And Giorgio, you guys don't count. Well, I mean, Argonne was the most advanced laboratory in the world when I was studying Mössbauer spectroscopy as a student. So this is a place where I wanted to go. And there was 2 guys there that were really interesting. One was called Stan Ruby, a totally crazy guy, who proposed that why don't you use a synchrotron source instead of a radioactive source to excite the nuclear transition. And he proposed this in '74. He tried 3 years, he didn't succeed, they fired him. And he had a heart attack. Then he left to another lab, right? My advisor, this morning I mentioned that listened to Stan Ruby's talk, and came back and worked 10 years and managed to succeed, right? And in the meantime, there was this guy, Kundan Singhvi, who was the advisor of my advisor, my boss, Gopal Shenoy. He wrote some lecture notes in 1967, which I saw in the library of Middle East Technical University in Ankara. All right? These were lecture notes given some ambitious graduate student called Gopal Shenoy took notes. Every night he went and typed it in his typewriter, and the next morning brought it in to be edited, and it became a sort of a hand-printed book, all right, which found a copy of its way to Middle East University. So I remember this curve, that this is the most power transition, but if you have the means, you might be able to use that very fine resolution, because that's 5 nano eV at 14 keV, all right, that's 12 orders of magnitude resolution. You can study phonons. So this was proposed, but nobody has ever seen it. So we went to Japan in 1994. I broke my leg because the traffic is in the wrong direction, so I stepped on the street the first night in Tokyo. But I persisted, and we managed to see, actually create a new field called phonon excitations by nuclear resonance scattering. So I'm going to spend a few minutes on that. Now, the key people, Mike Calvius was actually the origin of the Moscow laboratory in practical lab at Argonne. My boss, Gopal Shenoy. Harry Lipkin, maybe Kostas will remember Harry. We lost him a couple of years ago, but he was a very frequent visitor, and Gil Parlow. So basically what you do is you send the 14.4 keV X-rays, and this could be over 20 different isotopes, so I will only talk about iron, but we can do it for many other isotopes. You excite the nucleus. Right? Now you can say, how can you actually excite the nucleus with X-rays? Because nuclear transitions are typically in mega eV, right? Capital MeV. This is small keV. So there's like 3 orders of magnitude between nuclear transitions and the X-ray energies. But there are also, amazingly, even at the EV range, nuclear transitions that can take place. So one has to be careful when you make a generalization. Right? So the nucleus is about 100,000 times smaller than the electrons. So it's a tiny dot in a big universe. All right? But nevertheless, X-rays found their way and excite some of the energy levels. And when that happens, they release this energy depending on the lifetime. Right? So from there, we go and make a measurement of a molecule, and from these molecule phonon dense top states, I can actually see all of the atoms moving. So that's a 20-year journey. All right? Somebody dreams, somebody goes and makes instrumentation available for it, and then we say, okay, here's the capability. Some porphyrin chemists jump and say, can we use this? And then you say, well, what are you going to use it for? Because you have no idea that it can be used. And then all of a sudden you create a mini industry. So we published, of the 300 papers, about 100 of them are studying vibrations of molecules that are used in catalysis. It could be enzymes like hydrogenase, nitrogenase enzymes. It could be catalysis of oxygen reduction reaction or hydrogen reduction reaction. So there are so many ways you can use this method to study objects. So how does it work? You take the X-rays from the APS, you put it on an atom, you pump this nuclear energy level, which is at 14.4 keV. It lasts about 100 nanoseconds, and its width is 5 nano eV. Now you can say, how many photons do you have per nano eV? Because you had 10 to the 12 photons, 10 to the 13 photons per eV. Now you're talking about 10 to the 4 or 10 to the 3 photons left. All right? By the time the experiment is done, you're talking about 1 or 10 photons. And we are very good at measuring 1 photons per second measurements. All right? We published dozens of papers with a single photon, which means you have to have a detector that is millihertz background, all right? Which is possible. If you work at it, you actually build. So if you're in this business as a professional, you have to build your own crystal optics, you have to build your own detectors, you have to build your own software, and then make it available to everybody. And try to convince them that it's not scary, you can come and use it. All right? And so this was the first phonon dense top states we measured in Japan. And now we can take crystals like this and measure their properties and measure their entire vibrational frequencies. And then with the help of density functional theory, you can build a dynamical matrix, you can solve it, you can get the eigenvectors, which tells you in which direction and how much the atoms are moving. All right? So who remembers this guy? Well, this was the guy who discovered something at the age of 27 and got a Nobel Prize a few years later, Rudolf Mössbauer, all right? And if you take him, you will find out that he never used the Mössbauer effect as a name. He always used something called recoil-free emission and absorption of gamma rays by atoms, right? Of course, he used the German word Rückstoßfree instead of or Kernresonanz, right? Those were his words. But he got the Nobel Prize simply because not only he observed it, but he explained it. Because he came in after the Second World War, the nuclear research in Germany was extremely limited. He couldn't do nuclear research in a physics lab, so he had to do his research in Heidelberg in the medical school, even though it was physics, right? Because he was allowed to get a radioactive source in a medical lab, but not in the physics lab. And so in 1957, he came back to his advisor, Meyer Leibniz, who had many other Nobel Prize winners, and showed the results. And his advisor said, this is wonderful. You can publish it and get a job, or you can go back and explain it, which meant another 2 years. All right? But he did go back. He found a paper by Willis Lamb, understood the nuclear effect in the neutrons, and then applied it and came up with the idea and got the Nobel Prize in 1961. He was a postdoc at that time in Caltech. Richard Feynman hired him, and he made him a professor overnight. All right? So from very short postdoc career at Caltech. So we take these photons from the storage ring, we build these high-resolution tunable monochromators, which monochromates the beam down to 1 millieV level, and it's tunable. We focus them using X-rays, we put a high-pressure cell, we put detectors on the side and on the forward direction, and we make either a microscope or we make a spectrometer out of this. All right? So, to tame the X-rays, it's like taking Amazon River and putting a faucet in your kitchen. You can't do it in one shot. You have to do step by step, right? It's the same idea. We bring them through our high heat load monochromator, which deals with the immense power. Then you bring it down to millieV, and then you bring it down to 10 nanoeV levels. So you do it in step by step fashion. And you end up with 1 hertz. Starting from 10 to the 13, you go down 12 orders of magnitude. But that 1 hertz is a very good one. All right? It's not noise. So we start with kilowatts and end up with picowatts. All right? What do we do with this? So these are phonon creation and annihilation. Those of you who have done, let's say, Brillouin scattering knows the Stokes, anti-Stokes lines, right? You probably have heard of them, or phonon creation and phonon annihilation. You can create phonons, like here, you can annihilate them. If you, for example, cool this crystal or sample to liquid helium temperature, left side will disappear because there are no phonons to annihilate. Right? The phonons are bosons. I forgot to mention it. They can be created and annihilated. And the balance between phonon annihilation and creation is purely temperature dependent, given by the Boltzmann equation. Which means I can solve this for, if I measure the intensities, I can solve and measure the temperature. Now you can say room temperature, to measure room temperature you need $1 million instrument and a $1 billion machine. That doesn't make sense. But if you have a sample in a diamond anvil cell sitting at 3 megabar pressure and 2000 degrees, and you want to know what the temperature is on a nanogram or picogram material, there is no method to measure temperature except this in-detail balance. Right? So we use this to measure the melting point of iron and iron minerals inside the Earth at temperatures and pressures commensurate with the core of the Earth. Right? So it's used for that. Let me skip a couple of slides. So you can see we can convert this into desktop states. It's very nice. You can use it for many different problems. You can measure vibration entropy, specific heat, fractionation, kinetic energy. I mean, you make one measurement, but you publish 5 papers because each one has some specific interest to some specific group. So it's a very information-rich method. And as I mentioned, there are about half of the periodic table have Mössbauer transitions, but about half of them are observed using synchrotron radiation up to 100 kilovolt. We don't work with all of them. We selected a few, like tin, dysprosium, europium, iron, and krypton, and we make science using those isotopes. So this is how it works. You learn about optics, you learn about nuclear physics, you learn about accelerator physics. You have to convince the accelerators to fill the ring in a proper way. Then you develop your instrumentation, develop your software. So by the time you have done this, it's 20 years. All right? And now it's time to enjoy it, because you can actually use this for geology, mineralogy, material science, condensed matter, biology, chemistry. We do all of them because we have done our homework. All right? So it's time to enjoy the fruits of this work. That's what we're doing now. For example, for biologists, these bioatomic molecules are very important because taking CO or OH or O2 means either you breathe or you develop a disease, or it is the signature of everything is this, because heme group can associate all of them in your blood. All right? So when you breathe every single time, your iron in your heme group has a contact with the CO or CO2 molecule. And how does this work? Well, as I said, we can actually measure this. We can create enzymes that are actually mimicking those properties, and then we can study them. So development of a functional understanding of the molecular basis for selectivity is very important for understanding life sciences. All right. So I'm going to go a little fast because I would like to show you one example in, let me just skip. I promise you to go from atomic vibrations to asteroids. So I'm gonna show asteroids and then leave it at that because I'm exceeding my time limit. So just excuse me 1 second. I could go like 200 slides, so it's not a problem. So I sit between two beamlines that are doing imaging. And these guys make me jealous all the time because I get spectrum like one-dimensional, they get images, colorful images. Everybody comes and look at their posters and they look at, oh, that's interesting. So I said at some point, why don't I do imaging? All right? I mean, is it really difficult? Because I have this guy, all right, under my belt. All I have to do is build this and build a Mössbauer microscope. Right? Why not? I mean, it's in my hands. I have the beamline. I can do whatever I want. So I said, maybe I'll try this. So we take the monochromators, focusing optics, everything is there. We focus it down to, let's say, 5 micron. Put a meteorite here and measure it. Right? So that's what we did. When you do that, we measure many hyperfine parameters which help us identify certain minerals, because these are quantities that are specific to certain minerals, which comes with the data. So I went to a museum in New York, Natural History Museum. Then I wasn't satisfied. I went to Smithsonian, I met the curators, got something, and I went to Louvre in Paris, got some more, and we started the work on several minerals, meteorites. Meteorite is a meteor who actually fell on Earth, all right? And there are millions of them that fell on Earth, but as the size gets bigger and bigger, their numbers are very limited. So every year, meteorite hunters go to Patagonia or to Atacama Desert or Namibian Desert, and they hunt for meteorites, all right? So the museums are full of these slides in the back side. You have to be able to make the arrangement with the curator so you can go in the back and talk to these people. So here's an optical image of a meteorite called Estacado because that's where it was found. And so you can see that there are some metals and some non-metals. So I said, what is the Mössbauer image look like? Because this is iron map of the mineral, of the section. This is about 2 millimeters in size from here to here. So when you make the iron map, you can say, well, I'm going to go into this and this and this objects. and then you look at the mesh bar spectrum in the time domain, all right? And from these peaks, I can tell what is the magnetic field strength. And from that, I can say whether it's an iron nickel alloy. If it is an iron nickel alloy, how much nickel is in there. If it is a troilite, like an iron sulfide, I can identify that because each one has very unique signature, right? A non-magnetic phase like olivine or pyroxene will also tell me something. Something like hematite, which tells me that there's change since the meteorite fell on Earth. So I have done all of that. I was very happy with myself. I made a slide like this. I went to the chief curator of the Natural History Museum. He looked at me and he said, so you have identified minerals. What else is there? I'm speechless because, yeah, that's what I did, but obviously you can do some of that with an electron microprobe and maybe you can do it even better. So he was looking for something new. So I came back disappointed and started thinking about what can I do? What else can I do? So instead of putting the detector in the front, you put the detector on the side and you measure the inelastic spectrum from which you then calculate the force constant. And if you have the force constant, you have the isotope fractionation. Now that's something they cannot do. Because in order to do that, they have to cut this out and make a small sample and then make sure that it doesn't get contaminated with anything, put it into a most sophisticated inductively coupled plasma mass spectrometer, and if they are lucky, maybe a year later they get a number. Right? So now we are very, very popular with isotope geochemists because they all want to come and try something new like the tin isotope geochemistry, iron isotope geochemistry. So we said this is great. I mean, this is really encouraging. So my friend at Paris, at Louvre, wrote to me and said, what do you think if we get into this Hayabusa return mission analysis? Hayabusa is a probe that Japan has sent 2 years ago to an asteroid called Ryugu. All right, asteroids are objects between Mars and the outer solar system. There are how many billion asteroids, I don't know. But every now and then they find their way into Earth orbit, and then they fell as a meteor, and then they come into us as a meteorite. So this mission that went to Mars, to asteroid Ryugu, actually landed and drilled and collected some samples. And now it's returning to Earth. And there's big competition between isotope geochemists. Who's going to get these samples? Who's going to analyze them? So we said, we can do it. Of course, they don't believe you when you say that. Right? They say, prove it. Right? So they sent us some samples, unknown, and they wanted us to identify, which is very hard because there was no information whatsoever. So we analyzed them, we made some mesh-bar spectra that corresponds to this time spectrum, we sent it back to them, and then we got a letter saying, okay, you're in, right? Which means they were satisfied. So now we are waiting for this mission to come, and as you see, there are so many setbacks along the way, but if you are determined, if you say, okay, I'm going to succeed in this, you can actually get somewhere with it. So we are quite excited to be in the return sample, the return mission, which I would have never imagined that this would happen someday. Right? So, one last image. Do you know what this animal is, actually? It's a chiton. Chiton is a Greek word. Who's Greek here?
I am Greek, but I don't know.
Chiton means something inside the earth.
Chiton.
Yes, it means something that belongs to...
to...
Yeah, I'm sorry. Yes. There you go. Now we understand each other.
It's the English pronunciation.
You are Greek. I agree.
Okay. Thank you.
So we took this animal, and for 6 months we fed it with iron 57. Instead of the normal food, we feed it with iron 57 to improve the signal. Chiton is the animal that is known to eat rocks. Right? Because the tooth is so strong that they can eat rocks. But the dentists are always interested, what's inside this tooth? Why is it so possible?
I am a dentist as well.
That's there you go.
Additionally to my degree, I'm a dentist.
So you recognize this 66 or so teeth that comes out. So the tooth that is at the end is very, very strong. And my friend from Northwestern University, German friend, Linus, brought this sample and said, can you tell me what's how does this work? Because there's iron in this. And so we made a map of this sample, but of course you have to make a map that no one else can make. Right? Namely, I looked at, first of all, this response of the magnetite versus the ferritin. Right? Ferritin is a biological system which is not mineralized yet. Magnetite is mineralized. So if you look carefully, there's a region where there's a strong magnetite signal in time and no signal in ferritin. So we made an arrangement such that we only take the signal from this time window and made a map of magnetite and ferritin. So this was the first time a mineralogical map based on hyperfine interactions have been done. Right? So this paper is now in the manuscript form in some stage of publication. But you know, when you start the journey, you have no idea where you're going to go. Whether you're going to go to an asteroid or whether you're going to go to a chiton tooth, everything is possible so long as you master your method. All right? So my advice to you is, if you're doing it in infrared, do the best you can with infrared and look at what new applications I can push for. Because only then you will succeed. If you just repeat what someone else did, that's nice, you can get your degree, maybe you can get a paper out, but it's not going to get you anywhere. If you want to be famous like me, who is invited by nice people like Kelsey, right, you have to do something special. So I thank you for your attention.
Very, very much indeed. And I believe Professor Alp will take some questions.
I hope there are some.
Ercan, thank you very much. And it's really very impressive to go from let's say, the first trials and tribulations,
right,
looking at the progress of how we advance to a stage where we can actually have practical applications. Are there questions from the floor?
From one dentist.
Yes, please.
There's a dentist, I know
Yes,
that.
from the Greek dentist, yes.
Yes. So, I'm Professor Nicolucci, Nicolucci. I am a dentist, a stomatologist, I'm also an MD. I'm a cerebral pathologist and an embryologist stomatologist from my second degree. So I would like to ask you, inside those teeth, which is the difference that you had found in very strong tissues? It's like enamel. They have differences from enamel because enamel is the strongest tissue of all the bodies. So it has to be strongest than enamel.
Right. It's not just enamel. You see, the magnetite is actually the entire section is magnetite. So it's not just the enamel in the outside, but inside the teeth is also magnetite.
Inside the teeth, there is no dentin at all.
But it's just pure mineral.
Excuse me, I'm only asking if you have something, because I'm very interested in this, and this could be a very nice source for our project as well. We could analyze things, because in order to be stronger than all the teeth, it has to be stronger than enamel, stronger than dentin. We have enamel, dentin, and cementum inside there, and we have the pulp. It has to have the pulp as well, because otherwise we would not have any nutrition.
Right.
So, and all the origin of those tissues are from different layers in the embryonic body. So it's very interesting to know.
Yeah. So what I understood is that as you go along with this teeth, as they get older and older, the ferritin, which is the biologically living object, ferritin. No, ferritin. It's a mineral. It's an iron oxide, hydroxide mineral.
Excuse me, sideros?
No, ferritin.
Yeah, it becomes magnetite, all right, towards the end of its life, and that's the cutting edge of the teeth.
Instead that in aged people, we have loss of enamel. We do not have so strong tissues.
Yeah.
So that's very interesting.
Yeah.
We have to discuss further. Thank you very much.
You're welcome.
Other questions, comments?
The most common method is restrictive, right, to some isotopes.
That's right.
What do you do about the ones you don't know? The ones that you cannot analyze?
You just cannot.
So
We are lucky that iron was a gift. I wish germanium or silicon was a mass spectral transition, but it is not. So if you
have a sample, for example, with an isotope
Right.
that doesn't.
So I'm developing a new method called time domain interferometry to study those samples that are not including MESMAR isotopes, using the MESMAR transition and using the highly monochromatic beams. So it's something. I have a new PhD student since last year. We have done some early experiments. So there used to be a technique called Rayleigh scattering of the MESMAR radiation. So we are borrowing the book from them and creating a new kind of interferometer for those samples.
Other questions, queries, comments?
I think
It's been really a pleasure to have you here, and I think we are very lucky to have Professor Alp with us for the next days also.
right, I'm here, so if you have questions, please stop by.
And we also have a reception set out outside, so this is another chance to discuss in more detail over some refreshments. So I would just like very much to thank Professor Alp for making the trip and going through this rather sporty program today, which continues, as the Germans put it. This was an expression that I learned at a synchrotron radiation facility from a head beamline scientist who's German, and that was the first time I heard the expression sporty program, and I think we've managed to put you through that some sporty program, still smiling, so thank you very much indeed.
Thank you for
and
the
a show of gratitude. And we hope that all of you will join us to enjoy the reception outside and take the chance to